In our organic chemistry 1, we looked into definition of organic chemistry, terminologies in organic chemistry, hydrocarbons. There we even looked into alkanes, alkynes, benzenes, and we moved it further away from just the hydrocarbons to alkanols. In organic chemistry 2, we will be looking into alkanoic acid, alkanoids, fats and oil, amino acids and protein, carbohydrates, and polymer. In the last video, we looked into alkanol and we grouped alkanols into monohydric alkanol, dihydric alkanol, and trihydric alkanol. And in that monohydric alkanol, we saw that we have three types of monohydric alkanols, which are primary alkanols, secondary alkanols, tertiary alkanols in that monohydric alkanols. And in the presence of acidified potassium tetraoxomanganate 7 or acidified potassium heptaoxodichromate 6, the primary alkanol we know will oxidize to alkanal by removal of water molecule, which will be replaced by oxygen atom. Here, as I said that it is water that is going to be removed, that means that we can pick up H and OH. Hydrogen and OH group joined together will give us water. That is the water that is being removed, and it is being replaced by oxygen atom. And this oxygen atom has two unpaired electrons ready to be bonded. We can assume it is H and OH or H and OH that is being removed and replaced by O. But let me use this. It is this H and OH that is being removed and being replaced by O. When this is being removed, you know we have unpaired electron here, and this is from one atom. And this is also from one atom, oxygen. And oxygen is going to bond one atom. That means it's going to use the 2 unpaired electron to bond with carbon 2 unpaired electron, which is going to result to what we call double bond. And it will pull this here, and also change the direction of this. So we will have, knowing fully well that this alkana can still be oxidized further to alkanoic acid, it is said to be a reducing agent because it can oxidize further. Now, this alkana is still ready to be oxidized, ready to be increased further to give us what we call alkanoic acid. This is why we call it a reducing agent, or better, we call it a reducing sugar. That is why it can actually reduce the Valine solution and toluene reagent in the laboratory as a test for a reducing sugar. When it reduces Valine solution, it turns it to brick red, and when it reduces the toluene reagent, it turns it to a silver mirror-like precipitation you will see around the test tube if that is what you use. Do you get me on that? But in the presence of acidified potassium tetraoxomanganate 7, the secondary alkanols are oxidized to alkanone. This is also done by removing water molecule and be replaced by oxygen atom. So we will have alkanone. And this alkanone is mostly represented with this, but we can still represent it with this recro, where these are represent this H here. Hope you get that, because this will look as if it is fighting against the OH group, but here we are not showing that it's actually fighting against the OH group. Therefore, you can use this, but this is the one well accepted by chemistry teachers and WAEC, but this is still very, very important. This will help you to understand how the diagram look like, because comparing this and this, you understand how the diagram look like. I hope you get that. But these alkanones do not oxidize further. It is said to be a non-reducing agent. That means that it is a non-reducing sugar if, for instance, it is found in carbohydrate. When we are going to look into the carbohydrate, you understand what I am saying here. So, alkanone will have no effect on Valine and toluene reagents. I have a question for you. Alkanoic acids are said to be organic acids or carboxylic acid. They are actually organic compounds that have at least one carboxylic group as a functional group. I hope you know what we mean by functional group. I hope you know that. Okay, if you don't know that, I need you to go back to my terminologies so that you will get that. They are mostly found in the living and non-living things. They are mostly found there. And I'm going to be writing out some of them and where they can be found, including their possibly common names or old names. The first to look into is methanoic acid. It is actually found from bees and ant stings. Ethanoic acid. This ethanoic acid, another name for it is acetic acid, is actually found in vinegar. That is most alcohol that you take when you expose it to air and bacteria. Is going to convert that ethanol to ethanoic acid. That is why sometimes exposed palm wine tastes sour after some days, because bacteria were actually acting on it. Propanoic acid is actually found in fats. I don't know if you are noticing something here. The one we call methanoic acid, this does not have any alkyl group. I don't know if you get that. But the C of that is bonding to the O and OH is what we take as the first carbon. The same thing happens here. This is the first carbon. This is the second carbon. That means there are two carbons present in this molecule. And the same thing happens here. First, second, third. I hope you get that. So we go. In this place also, this is the first carbon, second, third, fourth. That means we're having four carbon here. So we call it butanoic acid. And we see this butanoic acid in spoiled butter. Ethane 1,2-dioic acid. Another name for it is oxalic acid. It is actually found in tomatoes. Mostly when you have a spoiled tomatoes, that is what you're going to see, the ethane 1,2-dioic acid. I don't know if you understand how we got this 2-hydroxyl butane 1,4-dioic acid. If, for instance, I number this 1, 2, 3, 4, you will notice that this OH is appearing OOH here. Here it is either 1 or 4, the same thing 1 or 4. That means if you are taking this to be the right counting, we need to consider if there is any other substituent here. There is a substituent here which is an OH group, the hydroxyl. Hope you get that. Now, this OH group, we need to consider the lowest value position it is. Now, if you are counting from here, we are having 3. If you are counting from here, it is 2. That is why we are saying it is position 2 hydroxyl. It would have been position 3 if we are not considering this idea of lowest value. I hope you get that, because some people will just count it like this and say it is 3 hydroxyl. Please, it is not. We count it from the lowest value. This is lowest to it rather than this that is 3. Okay, that's why I have it 2 hydroxyl. Butane 1,4, because the position of the OOH are at position 1 and at position 4. Hope you get that. Now, it's dioic acid because there are 2 acids, just like there are 2 acids here. 1, 2 means that the position is at position 1 and position 2. I don't know if you understand me at this point. Okay, that is how the name come to be. Another name for this is maleic. If we allow grape or apples to ripen too much, getting spoiled, the test we get is actually maleic acid from it, and the IUPAC name is 2-hydroxyl butane 1,4-dioic acid. We are going to stop in this 2,3-dihydroxyl butane 1,4-dioic acid. Whether we are counting it this side or counting it this side, it's going to be 2 and 3. That is the position 2 and 3. We're going to see hydroxyl group here, which is this and this, and it is butane 1,4 and dioic acid. We can see it in pineapples, grapes, tamarins, and other names of it is tartaric acid. Let's look at classification of carboxylic acids. Organic acids are classified into monocarboxylic acids, dicarboxylic acids, tricarboxylic acids. Very, very similar to that in alkanols, where we have monohydric alkanols, dihydric alkanols, and trihydric alkanols. And the primary alkanols is what we said that is oxidized to alkanoic acid in complete oxidation. That means that the secondary and the tertiary alkanols are not observed in dihydric and trihydric alkanols. That means that all the dihydric alkanols and trihydric alkanols are primary alkanols. I did not say that then, but I just need you to know this now. Let's start with monocarboxylic acids. Monocarboxylic acids are organic acids that have only one carboxylic group as its functional group per molecule of the compound. We have examples like methanoic acid, ethanoic acid, propanoic acid, butanoic acid. I hope you notice that I put 2 here. That means that this thing is appearing twice. These are examples of monocarboxylic acids. Benzenoic acid included, benzoic acid included. You know, benzoic comes from the word benzene. That is why you are seeing this structure here. Hope you understand me here. Let's go for dicarboxylic acids. Dicarboxylic acids are those organic acids that have 2 carboxylic group as functional group, the molecule of the compound. And we have examples like ethane 1,2-dioic acid, propane 1,3-dioic acid, pentane 1,5-dioic acid. Others may even have hydroxy group, as you can see in the previous work I did, like 2-hydroxy butane 1,4-dioic acid, 2,3-dihydroxy butane 1,4-dioic acid. You can include that in your work. Let's look at tricarboxylic acids. Tricarboxylic acids are those organic acids that have 3 carboxylic groups per molecule of the compound. And examples of them include, okay, this CH is the middle part of this, and this COOH is this value here. Okay, if you look at this very well, you will see that the propane we are counting is 1, 2, 3. It means that at position 1, 2, 3 of the propane, we are going to have 3 carboxylic acid, which are this. Hope you get that. I know this may look different from the ethane 1,2-dioic acid nomenclature. Yes, here they employed the idea of the common names. If we are actually trying to name this using the pure IUPAC nomenclature, it should be 3-carboxyl pentane 1,5-dioic acid. I know your question will be, your textbook is using propane 1,2,3-tricarboxylic acid as I showed here. Then why am I naming this 3-carboxyl pentane 1,5-dioic acid? If we spread this, it will look like this. This is how it will look like. Look at it very carefully. You will notice that this is 1, 2, 3, 4, 5, ignoring this. This is written as 1, 2, 3, 4, 5, ignoring this. Therefore, if we are counting 5 carbon, it is pentane, and the position is position 1 and 5. And it's actually a dioic acid in that sense. And we still have a derivative of carboxyl present that is found at position 3. That's why we call it 3-carboxyl pentane 1,5-dioic acid. That is if we want to name it using accurate and perfect IUPAC nomenclature. But your textbook WAEC will also use this rather than this. Therefore, still maintain on this, but know that if you see something that looks like this, then it means that the person is using the accurate IUPAC nomenclature of this. We have other ones like this. If we also want to name it perfectly like this, we are going to have a different name from it. It's supposed to be a different value entirely. First of all, let me draw the diagram for you before we name it using IUPAC nomenclature. Let's just give it its normal common names structure. As it is like this, it tallies with this. You know, this is position 2 here if you are counting it 1, 2, 3 or 1, 2, 3. But if we spread this by pulling this up, leaving this like this, just to look like this one, we will have. Notice the OH here is this. And if you count it 1, 2, 3, 4, 5. 1, 2, 3. That means the OH is at position 3. We are going to call it 3-hydroxyl. At the same place of 3-hydroxyl, we have a carboxyl group 2. But you know that C comes before H. Therefore, we're going to name this compound IUPACly. That is naming it using IUPAC nomenclature as 3-carboxyl, 3-hydroxyl, pentane 1,5-dioic acid. So, if we start from 3-hydroxyl, 3-carboxyl, it is wrong. This is the correct answer. Therefore, there's no need of me going further with this value. I hope you get that. We still have other ones like benzene 1,3,5-tricarboxylic acid. This is the best way to name this, although we can still name it a different thing because if you want to go with IUPAC nomenclature, this is not perfectly the real name. But I don't want to bother us on that because it's not much important, because most of our textbooks don't use that, and even the science world don't even stress themselves talking about the IUPAC nomenclature of this perfectly. Like I brought this thing down to this. Yes, they don't talk much about that. For we are going to pause here in tricarboxylic acid. Let's go for ethanoic acid, the special alkanoic acid. Ethanoic acid is actually the second member of the monocarboxylic acid, and the chemical formula is CH3COOH. Molecular formula is C2H4O2, and its structural formula is shown below. I want you to look at how I get it. This is actually the cause of sour taste of palm wine and mostly used as preservative and flavoring vegetable food. Let's look at the laboratory preparation of ethanoic acid. In the beginning of this video, I showed us oxidation of alkanols, the primary and the secondary, and the primary ended in alkana as impartial oxidation. The complete oxidation of this alkana will give us what we call alkanoic acid. Therefore, in the laboratory, we can actually prepare an alkanoic acid using a complete oxidation of primary alkanols to give us alkanoic acid. And here we are treating ethanoic acid. If we actually want to get methanoic acid, we can use a methanol, oxidize it to a methanol, which goes further to give us a methanoic acid. Since we are working with ethanoic acid, we are going to use ethanol, oxidize it, it will give us ethanol, then the final oxidation will give us ethanoic acid. I will not be going through this process again. I will just go to the complete oxidation rather than this partial oxidation. We will have this O is gotten from potassium heptaozodichromate 6 or even potassium tetraoxomagnesis or acidified. Hope you get that. Now that moves from ethanol to ethanol. This is the ethanol. So from this ethanol, we will have ethanoic acid. This is how we can prepare ethanoic acid in the laboratory. You can even be asked to state how to prepare a given alkanoic acid, starting from a given alkene. You may also be asked to prepare ethanoic acid from potato, which is starch. Starting from alkene, you need to understand that alkenes can be hydrolyzed by concentrated tetrodosulfuric acid to yield ethanol. Then from ethanol, we will have this ethanol. From this ethanol, we will have this ethanoic acid. The oxidizing agent we are using here is acidified. In the laboratory, the ethanoic acid is recovered using distillation. The acidifying is done using H2SO4 rather than the HCl. The H2SO4 is tetraoxosulfuric acid and the HCl is hydrochloric acid. This is because this hydrochloric acid is a volatile acid. And you know that you should not use any rubber during this because any hot ethanoic acid will attack or react with this rubber apparatus. There are other ways of preparing ethanoic acid, but the one much more used is bacterial oxidation of ethanol. Now, you know that we have actually done ethanol preparation from starch. Therefore, you can go back to that and answer that question that I say that they probably can give you. That let's look into physical properties of ethanoic acid. It is a colorless liquid, and I want you to know that the lower members of alkanoic acid are colorless liquid too. It has an irritating smell. By the way, the sour taste of vinegar is actually gotten from this ethanoic acid because the palm wine contains ethanol and bacteria which converts the ethanol to ethanoic acid that turns sour. Due to the presence of the OH group, it is soluble in water. The OH group constitutes what we call hydrogen bonding and is going to have a hydrogen bonding with water molecules. The numbers are not really important, but I just want you to know that it has a high melting and boiling point when we compare them with when we compare this ethanoic acid with other members of alkane, alkene, alkyne, even benzene. I don't know if you get me here. Okay, this is actually as a result of the carboxylic group that is present, and that carboxylic group contains hydrogen bonding. And I want you to know that the acidic property of this decreases. That is, they become weaker the more we have more of alkyl group. But if you have more of this, that is dioic or trioic, which is carboxylic acid present, we are going to have its melting point higher, solubility higher. Hope you get that. And there is a part of this ethanoic acid we call glacial ethanoic. It is actually an ice below 17 degrees Celsius. The more the carboxylic group presents, the more acidic properties are shown in alkanoic acid. Also, the more solubility or the more soluble the alkanoic acid are in water. Also, the more they have high melting and boiling point. But the more the alkyl group are present, we are going to have lesser solubility in water, and they become weaker in acidic, and also they have higher melting and boiling point. That means that higher melting and boiling point is a combination of the presence of carboxylic group and alkyl group can make that. Let's go for chemical properties of ethanoic acids. Just like other acids, they ionize in water, but this organic acid, ethanoic acid and so on, they ionizes partially in water. But let me tell you, methanoic acid is more acidic than ethanoic acid, because methanoic acid does not even have the alkyl group, and propanoic acid is less acidic compared to ethanoic acid. That means that ethanoic acid is more acidic than propanoic acid. This ionization shows that they produce hydrozonium ion or hydrogen ion in water. As an acid, they turn blue litmus paper red. They form organic salts when reacted with highly electropositive metals. Note this, when I'm using they, I'm talking about the alkanoic acid. That means that ethanoic acid is included. That means that when I use they turn litmus paper red, I'm talking of all of them. That means that we can just say ethanoic acid turn litmus paper red. The same way that it liberates hydrogen and also forms salts with highly electropositive metals. Remember, I can actually ask you a question, what will happen to propanoic acid when it reacts with sodium? Even WAEC can ask you that, NECO can ask you that. That means that any examiner or your teacher can ask you that question. Don't just depend on this. I hope you get that. That's why I'm using the word they. This is a neutralization reaction. This one you are seeing here is a neutralization reaction. They react with base to form organic salts and water. As you can see here, this is a neutralization reaction. Form salt and liberate carbon 4 oxide when reacted with any transocarbonate salt. Although sometimes it requires heating. I mean the alkanoic acids here, it requires heating sometimes. Okay, now we have treated the part where it is acting as an acid. So let's look at other properties of ethanoic acid. Ethanoic acid reacts with ethanol to form ethanoate in the esterification reaction, and other alkanoic acid can do same. We can have something like propanoic acid reacting with ethanol to give us propanoate. When we go over esters, I will explain more of this. And this reaction actually need increased temperature. That means it's an endothermic reaction and it's slow. But we quicken it with increased temperature and addition of concentrated mineral acid, mostly tetrodorsophaceous acid, because you know HCl, I said previously that it is volatile acid, and this reaction is a reversible reaction. This means that it can go in both ways. Hope you get that. And the product, which is ethanoate, have a sweet smell, and all esters normally have sweet flavors. That one is certain. Just like other alkanoic acid, they form amides with ammonia. Ethanoic acid also do the same. Ethanoic acid is not that easily to be reduced, mostly all the alkanoic acid. But if we have something like lithium hydroaluminate 3, it can be reduced. You get that? Now, this is ethanoic acid will be reduced to ethanol. That means that propanoic acid will be reduced to propanol. I hope you get that. and the propanol will be propan 1-ol. Butanoic acid will reduce to butan 1-ol, not butan 2-ol. I hope you get that with water coming out. Note that except methanoic and ethane 1,2-dioic acid, no other alkanoic acid can be oxidized further nor be dehydrated. Let me show you that of methanoic acid oxidizing and being dehydrated, and also show you that of ethane-dioic acid being oxidized and being dehydrated. This is even employed in production of carbon 4 oxide in the laboratory. Okay, the last point in this ethanoic acid is decarboxylation of ethanoic acid. Okay, it forms methane when it is being decarboxylated by heating it with soda lime. Something that looks like this is actually used in production of methane, but is a little bit different, where we actually use sodium ethanoate rather than the ethanoic acid. Summary of the ethanoic acid uses is, as you can see, used as flavoring and preserving food. I want you to know that this is very, very important. You need to have this in your memory. It serves as solvent for some organic substances. Yes, it is used in manufacturing of some chemicals like ethanols, esters. If you go back to that properties, you will see that it is used in making dyes, it is used in coagulating rubber latex. I am very, very happy to have you here till this end, and I urge you, if you are new to this my platform, make sure you subscribe. Click the notification bell for subsequent video updates, and don't forget to share my video to people. Share the links and inform them about what is happening. The next video will be going for alkanoids.